Hello, welcome to today's presentation on optimizing BigQuery. I'm your host, Christof von Rabenau. I'm a cloud architect here at Redapt and working in our advanced analytics team. I'm often brought into situations where organizations have adopted BigQuery and operate in the same way they would with a traditional row-based relational database. BigQuery is a column-based database, and as a result, there are some key things to keep in mind when you're actually running queries in BigQuery. What I've got today is I've got a presentation. I created a Jupyter notebook that will take us through various different approaches to how we can optimize BigQuery. So let's jump into things. I've created a Jupyter notebook that will walk us through various different aspects of optimizing BigQuery. The first thing, we have to actually create a connection to our BigQuery, and we're going to be using the Google Cloud Python API to connect to BigQuery. So this is a pretty handy way to deal with things, and if you're comfortable with Python and comfortable with Jupyter notebooks, it's pretty handy. So here we're making our connection to BigQuery. And then we have provided our project, and we create our client connection to BigQuery. Now, before we begin, understand that BigQuery charges based on storage and based on compute, or in other words, the data scanned. Storage in BigQuery is not the primary driver of cost, though it's not free. Primary cost is actually the compute. So all of the things that we're going to be looking at today, we're going to be looking at how do we reduce the compute load and therefore the dollar savings in our queries. What I've done is I've created a method that we'll use over and over that uses this functionality called dry run within the API. We can also do something very similar using the code validator in BigQuery console, and we'll touch on that a little bit later when we actually get into the workspace. So I've created this Python method that we're going to reuse throughout the presentation. And what it does is I've set the dry run equal to true. So we're going to be using the dry runs. We're not actually running the queries. We're just saying how many gigabytes of data do we actually use when we run this query. I've also set use query cache equal to false. This is one of the nice handy things about BigQuery is if you run the same query over and over within 24 hours, you run it on cached data, as long as there's no update to the tables that the data is coming from. So we don't want to be using it on cache. We don't want to be running on cache because we want to push every single time we run these queries. If it's the first time or the second time or the third or the fourth time, we want to be able to query against that. The other thing that I've done is the method also allows us to put a query to compare against. So when we do something that's going to optimize, we're going to compare that to the unoptimized query to make sure that we actually see some value in that. Now, the output of this method is kind of gross and rough. It's saying if we run this query once a day, every day for 30 days, how much is the usage for that? And then the estimated costs are based on the base of $5 per terabyte scanned. So it's just a tool to measure, but it gives us some way to measure it. So to start off with, we're going to use a couple of tables. One of them is big data, a fairly large data set from Stack Overflow, from the Google Cloud's public data set of Stack Overflow. And if we take a look, we can see this is the schema of that table. It's got quite a number of fields, various different types of fields. And if we look how many rows are in this data table, we can run a query to ask that question. And there are a little over 21 million rows and 36 gigabytes of data. We're also going to use the data set from Wikipedia, the Wikipedia page views on the public data set. And that's a lot fewer columns, but quite a number of rows. So here we've got over 55 billion rows and over 2 terabytes of data. So this gives us a good set of data to test our performance against. So if we've got the method here. I'm going to run that, and so we've now got this method within our notebook. We're going to look at the size of our initial tables. We're using the public data set from Stack Overflow. If we run that, we get a sense of what the table schema looks like and how many rows are in this table. We can run a query against that, and we get 21 million rows, 36 gigabytes of data. We're also going to be using, I created a data table off of the Wikipedia page views from the Google Cloud public data set. And that's got fewer number of columns, but a whole lot more rows. We've got nearly 56 billion rows and over almost 2.5 terabytes of data. We're going to do some baseline queries. We're going to select star and see how much does it look like if we select every column and every row and limit of 100 against that Stack Overflow database. We would expect that we're scanning the entire data set, so that's 33.8 gigabytes. And if we do the same thing against the page views, we get 2.3 terabytes of data. And this is going to cost us, if we ran this every day, it's going to cost us $338 a month. This one up here might not bring us much stress, over $5 a month, but $338 a month probably is going to cause a little stress in the system. So what about if we had our where clause? So that, here we're selecting everything. So seems like we should probably throw a where clause in there and reduce the amount of data that we're actually pulling in. So if we select a where clause, and compare that to our straight up select star, we don't actually see a gain on that. What happens if we do it against the large data set, the super large? No, still no gain. So the thing to understand here is the where clause still has to scan every row in that views, because we're telling it select star, so we're getting everything. So the thing to understand is select star is a BigQuery anti-pattern. You do not want to select star, especially on a table that's terabytes in size. So what we want to do is we want to actually only return the data rows that we're interested in our query. But you raise your hand and you say, hey, Chris, what about previewing the data? I want to get a sense of what the data is. That's why we run a select star. Well, BigQuery gives us the opportunity and the tool to look at that data. So if we go and look at our demo data set, and we go and we look at our post questions, right? Here's what the schema of that table looks like. Here's the details on that table. And then we can preview that data without actually incurring any costs. And so here we get our sense of the data. We can see what the form of the data is. We can see this creation date stamps and that sort of thing. So we get a sense of what the data looks like without actually having to query against it. So now we know our select stars are not doing us any good, and we know that select star is a big anti-pattern in BigQuery. So take a look at what happens when we actually select just the columns that we're interested in and compare that to our select star. So if we are selecting every row a select star, we're looking at almost 34 gigabytes of data in a month. Whereas if we only select the columns that we're interested in, it's significantly less. And the same thing happens to us if we do that on our Wikipedia. Now recognize the gain here isn't as significant, but remember there are only 4 columns in this table, and there are a lot more columns in the other table. But even still, it's a gain of a third. So definitely something we want to do. So now what happens if we put a where clause onto our query? In this case, again, we don't see the gain that we would expect. And interestingly enough, here, so in our previous where clause, we saw that we ended up having the same amount, the same scan of the data. So here we scanned the same amount of data. But with this one, what's happening here? This query, scans 1.018 gigabytes of data, whereas if we actually scan without the where clause, we're only scanning 0.317 gigabytes of data. The challenge for BigQuery here is we've added 2 new columns to the data that needed to be scanned. We don't have our comment count or our tags count or our tags within our select. So it's scanning 2 more columns of data. That's why we're seeing that increase of data. If we just put our where clause on one of the fields that we were returning, like view count, look, we can see we end up with the same amount of data scanned. Now, if we run our where clause against our big table, Again, we see the same performance whether or not we have a where clause or not. So now we're beginning to see ways that we can actually performance tune our queries in BigQuery. So first, select star is a big BQ anti-pattern. And then also recognize that where may not produce the payoff you expect if BigQuery still needs to scan the whole table, and it actually will cause you to scan more data if you're scanning rows or columns that you aren't returning in your select. So just be aware of that. So how do we actually get value from our where clauses? Well, that brings us to partitioning tables. BigQuery organizes data into buckets, and buckets, if you don't partition a table, BigQuery will bucket your data based on the patterns that are used to query the data. But you can enhance the partitioning by controlling it with either a time unit column, say you have a date stamp or a date or date time column in your table. You can also have it partition on ingestion time. So if you're streaming data, partition the data based on ingestion time. You can also provide an integer range and partition the tables based on an integer column. So what if we select, so I've created some partition tables. I took the Stack Overflow questions table and I partitioned it by comment counts. And now we can compare that partition request against a select star. So we'll select star from the partition table and compare that to the select star in a non-partition table. And we can see there's really not much gain in doing that. And likewise, if we do that against the partition against the Wikipedia, we don't see a significant gain yet. But now if we add our where clause to our select star, remember, here we're selecting all the columns, but we're going to add a where clause. Significant gains. So remember, our partition was on a comment count between 10 and 20. And if we go and look at that table, and look at the details, I've partitioned this table on comment counts, starting from 0 with a range end of 200 and a partition range interval of 1. So there are the questions with no comments would be in one partition, comments with 1, et cetera, et cetera. So what we've done here is we're now making a request against the table only between buckets that include comment counts of 10, 11, 12, et cetera, to 20. So now we're reduced the amount of data that we're scanning, and we're seeing that performance gain here. If we run that against the larger data set that I partitioned against views, again, look at that gain. That is definitely worth it. You know, if we're running, remember, this is just the select star, right? So I'm still selecting all the columns, but only data that matches views equal 100. So definitely partitioning your data is definitely a thing to do, right? Now, if we actually take that to the next level, and we've already identified, if we select the columns that we want, and now let's select those and add a where clause to it. Look at that gain. Look at the gain here. We're barely running a cost at all on that. And if we do the same thing on our large data set, again, very significant gains. So we can add partition tables to our key performance tuning. Now let's go and take a look at queries without limits. So notice in all my queries, I've limited it to 100. So didn't want to return a whole lot of data. So what happens if we actually query without a limit? Oh, look at this. There's actually no performance gain by using a query with a limit. If we do the same thing on our partition table, there's no gain. Why is that? Well, the limit in BigQuery only limits what's actually returned to you in the end. It still needs to scan all the data in order to aggregate the data as you would like it, and then it returns you 100 rows. So it's still scanning all the data, and we can see the same thing if we do it on our columns-based data in our partition table. So make sure that you're not relying on 100, you're using a limit like you would in a standard, in a row-based relational database. BigQuery is going to scan all the data first before it limits. Now, a case where you actually can get some value from limit is when you do an order by. So if you order the data and return a limit, you'll actually see some performance gain. So we'll add that to our key performance tuning. Limit clause will only limit what is returned. BigQuery still scans all the data. And I know that was one of the first lessons that I learned is when I was using BigQuery. I was told limit doesn't help you. So just bear that in mind. So there's another way that we can actually help return and limit the data that we're scanning, and that's with putting a cluster and a clustered index on a table. And so we've got our buckets, we've partitioned our data, and cluster actually organizes that data so that BigQuery can find the data more readily. So here I've created a clustered table. I'm clustering on tags, but to begin with, I'm not going to partition this table. We're just going to compare this to a non-clustered, non-partition table. So remember, this is a clustered table on tags, non-partitioned. So if we run that query, we see a nice gain. So what if we add a cluster to our partition table and we scan that? It's really not going to see, we're not going to see the gain that you might see because we've already reduced the data set and now we're just scanning pretty quickly. So that's not going to give us as much gain as we might see in a non-partition table. So, but remember clusters. So we're going to add clustering to our BigQuery tuning. Now, one of the things that Google BigQuery allows is wildcard table names. So here's an example. I've got BigQuery public data. It's a NOAA data, and this data goes back to 1948, I believe. So in this case, I'm saying scan all the data from all the data that you've got in all the data sets, all the data tables from 1900. And so if we run that, we're scanning about 1.7 gigabytes of data. Now, in the next query, all I've done is added a 7 after that 9. So now we're only looking at the data from 1970. And again, a significant gain. And then if we actually say specifically 1979, we see another significant gain in performance. So this takes us to beyond the select star is an anti-pattern to star being an anti-pattern. Be specific. So we're going to add be specific as possible at all times when you're making your query request to BigQuery. So you might want to select all of 1970, but make sure that that's exactly what you wanted to do and not just select 1979. Now, lastly, this is a little more complex concept, but this is a concept that you should really bear in mind as you're building your queries is how am I doing my work? So if we look at a sample data set from EPA air quality measurements from stations in Ohio, that data set is 1.7549. That data set is 1.479 gigabytes of data to scan this query. Now, we can cross-join that with cities in Columbus, Ohio, with utility information. So we can get a result back that tells us, what does it look like in Columbus, Ohio? Because in our previous query, all we've got is Ohio. But if we scan that against Columbus, we can get a result, and that scan is getting us 2 gigabytes of data. So all fine and good. But what if we want to do the same thing for Cleveland and Cincinnati? So here's Cincinnati, here's Cleveland. Each time we run this request, it's costing us 2 gigabytes of data scanning, right? So instead, what we want to do is we want to actually create a data set of the data that we're querying against as minimum as possible, but only the data that we're wanting to capture. So recognize that here we're looking for min extract, the minimum year, we're looking for the maximum measurement. And if we go ahead and pull just the data that we want into a table, this is going to cost us 10 gigabytes of data to do this, to create this table. So that's pretty hefty. But if we do that one time, and we scan Columbus, and we scan Cincinnati, and we scan Cleveland, and even scan Duluth, Minnesota, each time it's costing us less than 0.6 gigabytes of data. So if you're going to do this same query for more than 8 cities, you definitely want to materialize that data in a table first, rather than querying and hitting the table every time, the larger data set every single time that you run your query. So here you can see it's cost us a little over 10 gigabytes to materialize that data in a table. If we run it without materializing it 8 times, it's a little over 16 gigabytes. If we run it against the materialized table, it's a little less than 5 gigabytes. So in less than 8 times, in querying less than 8 cities, or a little more than 8 cities, we'll actually get a return on our investment of this initial investment of 10.14 gigabytes. So now imagine you're querying 200 cities across the United States. That savings is going to be significant. So in conclusion, we can say, here are 7 things to keep in mind when performance tuning BigQuery. 1, select star as a BigQuery anti-pattern. Select only the columns you need. Number 2, a where clause might not produce the payoff you expect if BigQuery still needs to scan the whole table, but partitioning tables and your where clause are your friend. So partitioning tables is another key performance tuning. Also, remember that a limit clause will only limit what is returned to you. BigQuery still scans all the data in all the columns first. Use the clustering on tables to improve your performance as well. Be as specific as possible at all times, and also look to materializing your queries in stages so that you can gain performance if you're doing the same query over the same data set multiple times. Well, I hope this has been helpful and brings you success with your BigQuery work. I look forward to hearing comments, and feel free to give feedback. Thank you.